lecture is going to be about Chapter 1. And Chapter 1 is about science. What are we talking about when we talk about science, and how is science different than other human endeavors? I want to begin by saying the very first section in the book, and I want you to read the book. Read all of the chapters that are assigned. We won't do every chapter in the book. There's not enough time. But the chapters that are assigned, they're not difficult reading. If you read them and you think about them, they're going to help you so much be successful on the homework and on the test. Okay. But if I tell you to omit something, you don't have to read it. The first section in Chapter 1 is about scientific measurements. And it deals with how some of the early geographers and scientists did things like figure out how large the Earth is or how far away the sun and the moon are. If you're interested, please read them, but I'm not going to put that material on the first test or the homework. Okay, so you can start just looking at section 1.2. 1.2 is about scientific methods. Oops, misspelled scientific. Scientific methods. Well, the first thing we want to realize is there's not one scientific method. There's lots of scientific methods. But for thousands of years, people didn't really do what we consider modern science. Later we'll talk about, in Chapter 2, Aristotle. Those were more what we call natural philosophers. Your natural philosopher looked at the world, and they made observations, and they thought about it, and they said, maybe it works like this. That's not really a scientific method because it's missing part of what we need. The thinking and making observations is a good start, but what they really needed to do was come up with a testable hypothesis, a scientific hypothesis. And then they needed to do experiments and measure what actually happened. And the person who really changed science for us is a man named Galileo. Galileo was the first person who really did experiments when he did science. And it was this very act of making a hypothesis and then saying, it's not enough for me to say, I think it works like this. I need to actually try and prove it. Okay. There are different parts of scientific method that most scientific methods will have. There's usually a question. There's something we want to understand. Why is the sky blue? Why do plants grow up instead of down into the earth? Any question that you want to ask based on observations. Then there's a hypothesis. A hypothesis is an educated guess. It cannot be a silly guess, or it's not going to qualify as a hypothesis. And we'll talk a little bit more about what makes a good scientific hypothesis. There needs to be some type of possible prediction. What are we going to check for? What do we think will happen? This prediction may be part of your hypothesis. Like I say, there's no one set of steps, but these are things that might be involved. There's often experiments. Or in the case of theoretical physics, sometimes you can't do a physical experiment, but there's mathematical calculations and experiments, so to speak. And then somebody puts it all together and comes up with a simplest possible rule of some sort. They pull it all together and they say, based on this, here's the rule. This is how things work. Now, usually what happens is you get kind of in a cycle. They make a hypothesis, they think what's going to happen, they do an experiment, and then they look at the results. They may go back and revise this hypothesis hundreds of times before they truly figure it out. Okay? So it's an ongoing process, but those things are typically involved. Now, one of the problems in physics is the words in physics may mean something different than the words in everyday language. Things like fact, theory, principle, law, they don't mean the same thing in physics that they mean when you're having a conversation. This shirt is pink. That's a fact. We'd probably all agree that this is a pink shirt. In everyday language, when something's a fact, the assumption is it's true, and it's always going to be true. In science, when something is a fact, it means that we have a lot of competent observers. Y'all are all competent observers, and you observed that this shirt is pink. Okay. If in the future, however, we find out for some reason our fact is wrong, we change it. The facts of science are evolving. It used to be a fact that a proton was an indivisible particle. That's not a fact anymore because we now know that the proton is made up of 3 quarks. For right now, a quark is the smallest part of a proton. That is currently the accepted fact. But again, that fact might change. So facts are our current observations that competent people agree on. But facts in science may change as we get more information. Scientific tools have allowed us to see things. We know much more about the nature of the moon than, say, humans did thousands of years ago. Now, in order to become a principle or a law, you have to have a hypothesis that has been tested and refined many, many, many times. When we reach that point and it's never been contradicted, the hypothesis can become a principle, or it may become a law. We have the law of conservation of energy. Energy cannot be created or destroyed. We've never destroyed energy, and as long as that's true, we've tested that so many times, we'll keep the law of conservation of energy. Archimedes' principle. Archimedes' principle says that the upward buoyant force is equal to the mass of the weight of the displaced water. That's been tested many, many times. So Archimedes' principle is a hypothesis that has stood up to the test of time and never been proven wrong. Now, what happens if you have a law, or you have a principle, or you have a theory or a fact that's proven wrong? Well, in the world of science, you have to change. Scientists change their minds all the time. Some people kind of think that's a type of failure, but it's not. It's a type of growth. If you're not open to new ideas and new learning, you're not going to be capable of doing good science. Okay. Now, the thing we haven't mentioned yet is, what is a theory? A theory is a synthesis of a large body of information. For example, in biology, we have cell theory. It's a large body of information about cells. In physics, we have atomic theory. We have the theory of special relativity. In everyday life, when people say, it's just a theory, they really dismiss it as if to say, oh, that's just one person's idea. But in science, when you say something's a theory, you're saying you have a large amount of scientific data to support this, that you, like I say, it's a synthesis of a large body of information. It's not just an idea that somebody threw out there. So if you casually say, well, that's your theory, well, that's not really a scientific theory. But a scientific theory is based on lots and lots of observations, experiments, testing, calculations, and review. And even so, it's still subject to change. Now, let's go back and talk just a little more about a hypothesis. A scientific hypothesis and that's really important. That's different than maybe just a casual, again, hypothesis. Must be testable. If you can't perform tests to see if your hypothesis is correct, it's not a scientific hypothesis. Not only that, it must be possible to prove it wrong. So it's not enough to have a hypothesis and be able to show that it's correct many, many times. But there needs to be some way to test it to see if it could be proven wrong. If we have a hypothesis that nothing travels faster than the speed of light, it's possible to prove it wrong. If anything ever does travel faster than the speed of light, we'll know that's a false hypothesis. At this point, anytime we've tested it, nothing has ever been capable of traveling faster than light. But it is possible that that could be proven wrong. If you have a hypothesis that you cannot objectively test, it's not scientific. You may have a hypothesis that natural blondes have more fun, but how are you going to measure and quantify how much fun different people have? On the other hand, you could have a hypothesis that says the percentage that redheads have a higher percentage of being, or greater chance of being left-handed than brunettes. And you could go out there and test it and find out if redheads are more likely to be left-handed. That's a scientific hypothesis. May not seem like anything very important to test, but you could test that. You could measure it. All right, let's look at some other ideas. What's the difference between science, art, and religion? And more importantly, can you believe in all three of them or support all three of them? Or do they somehow contradict one another? Most open-minded people see no conflict between the three. Science is studying your environment. Scientists study the natural world. They make observations and they try to make order out of it. They take this information and they explain, this is how the natural world, the physical world, seems to work. One person, and I did not come up with this myself, basically said science is about cosmic order. What is the structure of an atom? What is the structure of a solar system? How do baby chickens turn into big fat roosters and hens. All of those are about how the natural world works, and that is what science studies. Like I say, science used to be called natural philosophy, but it's what can we observe and how do we make sense and order out of it. We study the natural world all the time, and it's made a great many things possible. The arts, when I say art, I don't just mean painting. I mean literature, music, all the things that add beauty to our day. And your version of beautiful music may be different than my version of beautiful music, or I may enjoy reading different types of books. I may enjoy, different music, different literature, looking at different types of art. But all of those add beauty and enrichment. And so we often say that art is concerned about cosmic beauty. A lot of things in order to be successful really require both art and science. You know a lot of things. Being a good nurse is an excellent example, those that are in healthcare. Much of nursing is scientific. Most of nursing may be scientific, but there's still an art. There's an intuition. There's an approach to being a good nurse. These are not contradictory. If you want to be a truly well-educated person, you should study the arts and you should study science. And here comes religion. A lot of people, not a lot, but some people think that there's a contradiction. You cannot be scientific and be religious. And it's simply not true. Many scientists are deeply religious people because those are two separate human activities. Studying the natural world is one thing, and worshiping, most religions worship a supreme being, that's something else. And they're not a conflict. Religion isn't about cosmic order or cosmic beauty per se. It's about cosmic purpose. Why are we here? Why is there a universe? Why did God create the universe? Why did God create me? What am I supposed to do with my life? How should I be living my life? What's right? What's wrong? Those are entirely different questions than what's the structure of an atom? How do baby chickens grow up to be hens and roosters? Okay. So truly open-minded, educated, thinking people will study all of these things and make their own choices, particularly about things like religion. Okay. So, all three important, but all very different. Finally, there's one more idea that we want to talk about, and that's technology. I'm going to say that science is a body of knowledge. We know all kinds of scientific facts. We know lots of chemistry, lots of biology, lots of physics, okay? Lots about anatomy and physiology, all kinds of information. Technology uses science for some purpose, usually to make our life easier. So technology, I said uses science, a better word probably would be applied science. So technology is applied science. What do I mean by applied science? We use science to invent the washing machine. Washing machines have made our lives easier. We've used science to make cell phones. We've used science to get fossil fuels. We've done all kinds of things to make human life better using technology. But technology is kind of a double-edged sword. We have to be careful how we use it. Fossil fuels, which are used to make gasoline, have made transportation amazing for us. We have cars, we have planes, we have boats. We can get where we're going if we're not in a pandemic. However, they've also contributed a lot to pollution, to air pollution and smog, and to climate change that we are studying now. Cell phones, they're pretty wonderful for communication. They're so smart, we can look up things we want to know just like that. However, we do need to be careful. Children with cell phones, they are impacting how children think and how their brains work. We need to be really thoughtful in our use of technology. So, technology isn't good and it's not evil. Technology is just human beings taking their scientific knowledge and applying it to other purposes. As long as we're thoughtful, technology is wonderful. Technology is going to be what ends the current COVID-19 pandemic, because technology is going to be how we develop vaccines and other medical treatments. Technology is how we have ventilators that have kept patients alive, excuse me, some for over 30 days on a ventilator, and then they've gotten well and gone home to their families. Okay, so chapter 1's just one more big idea in chapter 1. I almost forgot it. Physics is the most basic science. It's the most fundamental one, and I'll try to explain why. Physics is the study of matter and energy and the interaction between them. Well, matter is the stuff everything is made of. You're made of matter. This eraser is made of matter. That tree outside my window there is made of matter. So when we say we're studying matter, we're saying we're studying all the stuff in the universe. And energy is how that stuff changes other stuff. Takes energy. So we're talking about all the stuff in the universe and how all this stuff in the universe is interacting with the other stuff. That's pretty basic. If I was building a platform, here's physics. Now, one thing that physicists study is electromagnetic interactions and electrostatic interactions, and those electromagnetic interactions are responsible for all of the bonds in chemistry, all of the interactions in chemistry. So chemistry is really just a little subspecialty of physics. How plants and people and things grow and develop, these are both considered our physical science, our life sciences. depends on both of these. So I would put biology even up here. Another way you could think about this would be a Venn diagram. Everything is physics. But there's a small part of physics that is chemistry, where we're studying chemical compounds or different elements, whether things are solid, liquid, and gas. And a large, small part of that, I would say, is biology. Notice some aspects of biology fit more inside of physics than maybe chemistry, like your nervous system, which is electrical in nature. So, if you're studying science, physics is the most basic, all-encompassing of the sciences. And we're just going to study it at a conceptual level, the most basic, big ideas in physics, without all of the complicated mathematics in physics. And that is the end of chapter 1. There are some PowerPoint slides available, both ones that I've written and some from the manufacturer you could look over. And of course, you've got your chapter 1 Mastering Physics homework to complete.